Stage lighting, like other technical roles, is a practice-based skill, where the knowledge of how to rig and operate stage lighting equipment is needed in order to produce creative lighting effects. Typically, these skills are developed in vocational training contexts, where students have hands-on opportunities to work with professional equipment and learn through engaging in deliberate practice, a cycle of highly structured activities and immediate informative feedback from experts, the explicit goal of which is to improve performance. Being able to support the teaching of stage lighting in the K-12 creative arts classroom could provide opportunities to engage in STEAM, a movement to embed science, technology, engineering and mathematics teaching within the arts. However, while the creative arts are taught widely in K-12 schools, their curricula typically don't include the opportunity for students to gain skills in technical roles. Mainly because of the constraints of the classroom, we designed a toolkit centred around tangible hardware proxies to support the development of practice-based skills in stage lighting within the constraints of a K-12 classroom. We looked at the way professional practice is able to offer ways for lighting professionals to access equipment and training. This is typically done through the use of simulations, with common examples such as Show Express and SIGCHI. These simulations, however, are designed with the professional lighting designer in mind. As such, they assume a pre-existing knowledge of basic lighting fundamentals and equipment, and therefore are not suitable in supporting novice learners. It was clear from work already done in tangibles that consideration of representation is key in any design of tangible interfaces that aim to support teaching and learning. Price highlights 4 specific features that should be considered: location, dynamics, correspondence, and modality. As yet, this framework has only really been applied to contexts where representations of abstract concepts have been designed and evaluated. Examples of tangibles being used to represent real-world interactive objects is less common, although there are some notable examples such as Schneider et al.'s work with Tinkertable, which uses tangible interfaces to teach vocational skills in a manageable setting. Artifact representation is still fundamental in this context though, as we know from previous work that this can affect learning outcomes. We needed the toolkit to support, firstly, vocational learning, which meant finding ways to support hands-on deliberate practice and student-centred pedagogies. Secondly, we needed to support skill development outside of the primary context. This required us to support students gaining understanding of the fundamental skills needed for stage lighting. We then needed to support learning specifically within the K-12 context, and this meant being aware of the physical constraints of the classroom, as well as time constraints of lessons. And so the toolkit, for example, needed to fit on a tabletop and be able to be set up and packed away easily. Finally, and most importantly, we needed to support students' transition to real equipment, something which has proved to be a challenge in other contexts that use tangibles to support teaching and learning. We created a toolkit of resources based around the use of tangible hardware proxies. We've used the term proxies here to describe tangible representations of stage lights within the toolkit. These differ from solutions offered in other models, simulations, or virtual environments for stage lighting, as they are designed specifically to substitute one-to-one for real pieces of equipment without the complexities of high-fidelity simulation, to model only certain properties of the equipment that would enable skill-based practice. So, for example, in this case, the optical properties were modelled, but not the weight or specific cabling for stage lights. And finally, they were designed to be incrementally switched out for real equipment. Stage lighting is controlled using an industry-specific, one-directional protocol, usually referred to as DMX. As a minimum, there were 3 aspects of this protocol that we needed to model. Firstly, channels. DMX protocol works in groups of 512 channels, which are referred to collectively as a universe. Each channel can be set to any 8-bit value, so values between 0 and 255. This value is used to control individual properties of stage lamps. Some lamps take up a single channel, while other lights work with multiple channels. Secondly, we needed to model RGB colour mixing, another real fundamental of stage lighting. And finally, students needed to understand how to address lamps so that when they are controlled, they behave in a way that is expected. The toolkit we created consisted of 3 types of tangible proxies, plus a broker and scaffolded pedagogical activities that helped guide students to engage in deliberate practice. We will have a look at each element of the kit in turn. The hardware proxies were developed to be small and usable on a tabletop while modelling key characteristics of stage lamps. They are all controlled wirelessly in order to ensure students concentrate on the lamps and the controller rather than ensuring the cabling is correct. These proxies all contain a BBC microbit, which runs a Python application. Each device is battery powered and has at least one LED connected to the I/O pins of the microbit. The channel can be changed from the back of the proxy using the A and B buttons, and the current channel is displayed on the microbit screen. This is similar to the way that a stage lamp would operate when adjusting their addresses. we created 3 different types of proxies, each representing a particular stage lamp. The first proxy was of a single channel lamp. Our implementation has a single white 5mm LED with a 9-degree angle of projection. The second proxy is of an RGB colour wash lamp. Our implementation has a single surface mounted neopixel RGB LED. A lens is attached over the LED to give an unfocused pool of light. Each colour in the neopixel is controlled by an individual channel, channel 1 controlling red, 2 green and 3 blue. This allows for complete control over colour mixing in the same way you would with a real lamp. The third and final proxy is of an RGB multi-colour wash lamp. Our implementation uses a neopixel strip of 8 RGB LEDs, with each LED able to be controlled individually. When students use the control desk, these proxies mirror exactly the behaviour of a real stage lamp, so that students can experiment with lighting designs and control functions. Alongside the proxies, we created a broker that is the linchpin of the toolkit, and it supports student transition from proxies to real stage lamps. The broker is a portable unit that is mains powered and acts as a bridge between existing industry stage lighting protocols and the proxies. It is this unit that allows for the flexibility of swapping in and out the proxy lamps and the real lamps. The broker contains a Raspberry Pi running open lighting architecture software. A Wi-Fi access point allows for control devices to connect to the broker over SACN, OSC or ArtNet protocols, all industry standard. 2 NTEC DMX Pro devices are attached to the Pi to allow for DMX input and output. This is where real stage lamps are connected as outputs and will also allow physical lighting desks to be connected as inputs. The Python script running on the Raspberry Pi receives updates from the Open Lighting Architecture API and emits them via the USB serial to a BBC microbit connected to the Pi. A second Python script on the microbit broadcasts this information via its radio functionality to any microbits in range that are acting as proxies. This effectively creates a low power and wireless DMX universe, which can then be controlled by any software or hardware DMX lighting controller. Using this broker means that real lamps and proxies, as well as physical and digital lighting desks, can be connected to the broker in many different configurations. For example, students can use a software controller such as LightKey to control proxy lamps connected to the broker. In the same way, a hardware controller, a physical lighting desk similar to the ones in venues, can be connected to control the proxies. Proxies can also be swapped out for real lights to facilitate the transition from proxy to real lamp. Here, we can see a software controller being used to control several proxies and a single real lamp, allowing students to create mental models of the behaviour of real lamps in relation to the proxies. Finally, there are a suggested set of tasks for use with the toolkit that scaffold the learning of various fundamental concepts within stage lighting. These tasks are designed to encourage students to engage in deliberate practice with goals and clear opportunities for feedback. Our prototype was used in 2 public high schools in the UK, and in each school a small group of students were tasked with designing, planning, programming and operating the venue lighting rig for a live event at their school. These students were given the toolkit and worked mainly independently, using this to firstly practice their skills and later to design, plan and program the lighting for the event before transferring their skills to the real lighting rig on the day of the event. Following these deployments, we found that these proxies can be used to support the teaching of practice-based skills through risk reduction. Our findings indicated that the use of tangible proxies to scaffold the learning process reduces both the real and perceived risk for teaching staff. The size of the proxies meant that teachers were able to move the teaching of these skills back into the more controlled environment of the classroom, putting the teacher back in control and allowing them to focus on supporting student learning rather than worrying about logistic or health and safety concerns. The relative inexpensiveness of the proxies meant that students had an opportunity to prove their skills and ultimately led to a greater trust between student and teacher, which encouraged the teacher to allow students to use the real equipment autonomously in the final event. The proxies supported flexible reconfiguration, which allowed development of conceptual learning. So, as students progressed through the higher level design tasks provided by the toolkit, Broker acted as the anchor, which allowed for a graduated transition between the controller's prototype lamps and real lamps. The use of these tangible proxies supported independent learning, as well as allowing them to engage in rapid experimentation, which would not ordinarily be possible with real lamps. This experimentation and the rapid iteration meant that students were able to develop the requisite mental models of the way the equipment operates, and therefore they could understand both the technical limitations as well as the creative possibilities they afford. Finally, the broker acted as a route to new pedagogies. Without the broker, tangible proxies are essentially just low-fidelity models of stage lighting equipment. The broker is ultimately what provided the bridge between industry standard software inputs and hardware proxies, and is what enabled the development of stage lighting skills. Designing hardware proxies to support practice in these scenarios involves identifying specific skills that need to be supported in deliberate practice, mapping the properties of real equipment that need to be represented in models, and the constraints of using the real equipment in the classroom, and finally, identifying which control or representation protocols the broker needs to support the practice of these skills. We saw that the broker opens up new possibilities for developing innovative pedagogies within the classroom, as it allowed for multiple students to interact with a single representation of a venue, something not possible with the real equipment. This then offers the possibility of using the proxies to support co-located, collaborative environments in which to learn practice-based skills.